All right, so this is the last part of the Chapter 2 lecture series. But this is not in the book. So we've talked about, stress and strain and all of those kind of things and material properties. Now we're going to apply that in the case of a very simple structure called the cantilever. So a cantilever is basically a beam that's attached on one end. So in engineering, we call that a cantilever. And if we attach a beam on both ends, we call it a bridge. Okay, so there are lots of examples of cantilevers in the real world. Things like airplane wings is a cantilever, right? It's attached to the fuselage of the plane, and then the other end of the wing is off in space. So you can do some modeling of airplane wings, for example, using basic cantilever physics. Other cantilevers could be, say, a diving board, right? That's a classic one. We're all familiar with diving boards if we've been around swimming pools. Antennas, right? They're attached on one end and they're free to move on the other end. So that's basically what a cantilever is. So if we look at a cantilever, we can take it and we can displace one end of it and let it go and it'll vibrate. We can also put a weight on the end, as it is in this photograph here, or this sketch, and your cantilever will bend. And it'll bend depending on a few things. One is the weight of the mass you add onto the end, or the load that you apply to the cantilever. And the other aspect is, what is the springiness of the cantilever? How stiff is it, right? So that's the spring constant, K. So you can see here from basic physics class, there's Hooke's law, F equals minus Kx. And what that means is if we apply a force to a spring, okay, we're going to displace it by an amount that's equivalent to the product of the spring constant and the displacement that we put on it. So the more force we put on the spring, the more displacement x we get for a given spring constant. Okay, for a cantilever, the spring constant is found by taking the elastic modulus E, which is the material property. You'd figure it has something to do with materials, right? And you multiply by some dimensional properties. So we've got the width of the cantilever. Okay, it's shown in this figure here. We've got the thickness of it. In this case, it's D. And the length of the cantilever. That's the length from the edge to the end of the cantilever. And that's the spring constant. Now, spring constants are going to look different depending on the shape of the spring. Okay? And you can generalize it with the moment of inertia as well, but we don't do that in this class. We're going to just worry about one type of shape, which is the rectangular solid. So something that's long, not too thick, and has a certain width. So here again, this is the K for the cantilever. Okay? And these are the equations that you saw in the previous one, but there's another equation, the resonant frequency. So if we displace the end of the cantilever and let it go, it's going to vibrate for a little while until it damps out and stops. And it has a natural resonant frequency. So you hit it and it's going to vibrate at a certain frequency. You hit it, it's going to vibrate at the certain frequency again. Okay, so it's kind of like a musical instrument. If you've looked at jaw harps, they're cantilevers, and you can amplify the sound by changing the shape of your mouth and all of that. But the resonance of the jaw harp, the little vibrating piece that's inside the jaw harp, stays the same, and it only changes as a function of the geometry. All right, so here we have the resonant frequency, and that's the first harmonic. You can get things to resonate at higher harmonics as well. We're not going to talk about that in this part of the lecture. Okay, so omega naught is the frequency the system wants to vibrate. And if you measure it, you're going to measure it in hertz, and that's F naught. That's the frequency you measure it at. So omega naught is in radians per second, and F naught is in cycles per second. So that's why you have that 2 pi in there. Okay, so if I do a measurement in the frequency, that's F naught. That's going to equal 1 over 2 pi times the square root of K over M. And M is the mass of the cantilever. So you figure out the mass of the cantilever by either weighing it, or if you know the density of the material, you can look at the dimensions, you know, the width, the length, the thickness, right? That gives you the volume. You multiply density times volume, and you get the mass, okay? But you can look at this, that there are 2 parts to the resonant frequency. One is the material properties themselves, which includes the density of the material and the elastic modulus, and then the shape of the material, the thickness, the width, and the length. Okay, so if we combine these two together, okay, we substitute in for K, and we get something like this. Okay, and I want you to do this on paper and go through the math so you can generalize this even further, and we're going to do that here. So if we simplify it, we get something that looks like this. You can see there's a mass in here, there's a length cubed, there's a D, which is the thickness, and W is the width, okay? And E depends on the material. So if you have something stiff, the elasticity is going to have a bigger slope in the stress-strain curve, a higher slope, so this number will be bigger. And that's in pressure units, right? Megapascals. So if you do a unit analysis of this, use megapascals and all of that, you will get something that looks like 1 over seconds. All right, so let's take a look at this. So assuming I'm going to go get my pen. Assuming that we're going to just change the length of the cantilever, what do you think will happen to the resonant frequency? That's the frequency it wants to vibrate at. So if I make this cantilever longer, or if I make this diving board much longer, what do you think will happen? Will the frequency get faster or increase? Will the cantilever slow down, or will it stay the same? Well, if you think about it, and you can play with a ruler or a stick at home that has some flexibility to it. If it's too stiff, you can't observe it very well. But you can clamp down one end of your stick on the edge of a table, for example, with a standard C-clamp, and then hit the other end and watch it vibrate, and then make it longer and see how it vibrates, and make it shorter and see how it vibrates. I usually do this live in the classroom, and you'll find out that the longer it gets, the slower it gets. Now, if you look at the math, that makes sense, right? The length of the cantilever, L, is in the denominator. So if this goes up, right, the frequency will go down. Okay, and it's a weird relationship, right? It's 1 over L cubed underneath the square root. You'll find out later that, you have to put in information about M, and then you get even a better equation. All right, so now we're going to change the thickness of the cantilever. Well, that's in the numerator. So if my thickness goes up, then my frequency should also increase. Okay, and that's what you should always do with these simple equations, is just look at what happens. If I change this, what do I expect? If I change that, what do I expect? And get a feel for what you would expect to happen. And then that way, when you do your experiment, or you're utilizing a cantilever sensor for something, or designing a cantilever to be part of a system, or if your system has a cantilever in it, you have to think about the resonant frequency and what happens if it gets longer and if it gets shorter and that sort of thing. And you do that with other systems and other equations. Okay, so if the thickness goes up, we'd expect the frequency to increase. And if the length goes up, then we expect it to decrease. All right. So now what about the width? And now in class, I would have you guys actually do this experiment with a set of cantilevers I've made. They have different widths, different thicknesses, and then you can decide how long to get it by how you clamp it to the table. And when you do this experiment, you would expect, just glancing at the equation, right? You'd expect that when the width gets wider, the frequency should get higher, right? That would be what you would expect just by looking at the equation. But the experiment shows that there is no change in the frequency. And now you're going to scratch your head and go, how is that possible? There's a W here. This is material property. That's not going to change with the width, right? But you have to think, what else changes with the width? The mass does too, doesn't it? Because your cantilever, okay, is a beam that looks like this. Okay? Right? And if I make it longer or thicker or wider, right, what's going to happen to my mass? It's going to go up. So if W goes up, width, the mass also goes up. And you'd say, hey, wait a minute, Dr. Plyle. If the length goes up, the mass also goes up. And if the thickness goes up, the mass also goes up. How come those frequencies changed? And you'd observe that if you do the experiment. How did those frequencies change, but not with the width? But now you look at these exponents here. This is to the cube, this is to the cube. This is only to the first power. So think about it. If I double the width, right, I'm going to double the mass. Because what is the mass? The mass is the density, right? That's supposed to be a rho times a volume. And volume of a rectangular solid is the width, x, y, z, okay, or width times length times thickness. All right, so now you've got a width in here, right? So the two widths cancel out, and we'll show that in the following slides. Okay, so why does the frequency not change when one widens or increases W? Because we got to consider the mass. The mass is rho, the density, times the volume. Oh, look, here's another material property. Okay, and this is a geometric property. You'll find so much in mechanical engineering that has a material property component and a shape component. And you as a designer may not be able to change the material you work with, so you have to change the design to adjust for different frequencies, for example. All right, so we back substitute in for the volume, right? It's thickness times length times width. Okay, we put it in the equation. I'm just doing this in gory detail so you can see what's going on. Okay, so notice that it went to L to the fourth because width times distance times length times L to the third is L to the fourth, so follow along. Okay, now you're going to say, oh, we can get rid of a D, right? And we can get rid of a W. Oh, look, there's no more W. So we got rid of the W completely out of the equation. Okay, so that means frequency is not dependent on the width. And that's a good thing when you're a designer. Okay, so we do the simplification and we get something that looks like this. And now what happens when we change the width? Well, there is no W in the equation, so there is no change. Okay, so again, we can simplify some more. Okay, we've got a square here and a to the fourth here and a square root, so we can take those out. And now we've got something that looks like this. So we've got thickness here in the numerator. So if I double the thickness, I double the frequency. If I double the length, I go down to a quarter of the frequency. So now if you look at the frequency versus length curve, it's going to look like, whoa, it's going to kind of look like this. Okay, it's going to change a lot, and then as it gets longer, not as much. It's a 1 over r squared kind of relationship. But if you look at frequency versus D, and let's make D a different color. I like blue. It's going to look something like this, a straight line. Okay? So that's what you would expect with the math. And if you actually do the experiment, right, you will find out that this is true. There's slight variations because you have damping from air, so it affects the frequency a little bit, but to the first order, it's pretty solid. All right, so this is a nice equation now. We've got everything here. That's geometry, so this is what you do as a designer. You change these values here. So this is geometry, right? Shape, whatever you want to call it. Geom. And then these numbers here, this E and this rho is all material property. So if you do have a choice as an engineer to change the materials for your given application, you can find certain materials that'll fit your design if your design is constrained to a certain geometry. Okay, and you need to get it to a certain resonant frequency. All right, so here we go. This is a nice clean version of my scribbles from the previous slide. You've got material properties and you've got dimensions of the cantilever. So now you can go forth and design different things to work differently. So here is a link to a YouTube video one of my colleagues from Ivy Tech put together. It's using SolidWorks, and you can draw a simple cantilever, assign a material to it. You can fix one end of it, and then you can look for different resonances. So this is the first order resonance here, which is 5 hertz. And you know, I have a kit that I put together for technicians and engineers to learn about cantilevers and do the experiment in the classroom. And you can measure the resonant frequency using a video from your phone, and then you plot the resonance as a function of length, as a function of width, and a function of thickness. And then you add some mass to the end of it, and then you can turn it into a scale, and it works out really nice. So you can go ahead and model it in SolidWorks, and you get very close correlation between, you know, the modeling and what really happens. But you always want to verify with experimentation that your models are correct. Okay? All right, so here's another video. We could probably go ahead and, let's see. We can probably go ahead and watch this video. So this, you know, we talked about thickness, length, and width, and how it affects the resonant frequency of a cantilever. You can use a cantilever to determine the mass of something. So what you do is you create a cantilever and you add mass to it, different amounts of masses, and then you plot the frequency versus mass added to your cantilever. And then when you have an unknown mass that's added to the cantilever, you can determine from the frequency shift, right, the resonant frequency shift, how much mass you added. This is really good to do with micro-cantilevers if you're looking for a certain, say, virus, or you're looking for a certain bacteria or a certain chemical. You can coat the cantilever with something that only that chemical or virus sticks to, like a certain antibody. And then if the virus comes by and it sticks to the cantilever, the resonant frequency of the cantilever will shift. And as a result of the shift of that resonant frequency, you can tell that 1, you detected the virus, and 2, by the amount of the shift, you know how much virus you've detected. Okay, so this is kind of a fun video here, and I'm going to go ahead and show you that, and then you'll see what happens. So basically, when the video is played, you'll see that this child is at the end of a diving board and bouncing up and down at the end of a diving board, and then his father comes on the diving board and picks him up, and you'll see the resonant frequency shift. Okay, so here you go with the video. So that was a good video. So it makes you think a little bit. So here we have some real cantilever arrays. These are very small. You can see in the corner here. Right, this is 500 microns, this length right here. So these are about maybe 750 microns long, if I had to guess. Okay, so that's less than a millimeter, right? So very, very short cantilevers. And then this company will coat them with different things. So on this one you might put, say, an antibody for corona. Okay, and then on the other one you can put the antibody for, I don't know, SARS, et cetera, and then you'll have a couple of, ones that you have as a control to make sure that everything's working right. And then you get these oscillating, and if one of them shifts, let's say this one shifts, okay, in frequency, then you've detected SARS. And if this one shifts in resonant frequency, then you've detected COVID, et cetera, et cetera. Okay, so you can have all the cantilevers the same length and coat them with different things and have a couple of controls in there so you don't get false positives. So that's one example. Some chemicals and some things that you're trying to detect work better than others. I've seen data from a PSA, which is a prostate antigen kind of thing, where they use it to detect prostate cancer, and then I've seen another application where they looked at the bacteria that causes severe diarrhea, right? What is that called? E. coli. So they created a cantilever that E. coli sticks to. And they can detect one E. coli bacteria, and it'll be a really slight shift in the frequency. All right, so here's an iClicker question. We have this cantilever over here and this cantilever over here. Which one will have the lower resonant frequency? All right, remember what we said about L. Where is L in that equation? In the numerator or in the denominator for the resonant frequency? All right, well, you should know that the longer the cantilever, the slower it gets. And you can kind of envision that in your head, right? You have experiences with long boards and things like that, so you probably have a gut feel which way it should go. So here's an example of a real cantilever device, right? If this is a scanning electron microscope, so this is the end of a cantilever right here. And that's made out of aluminum, and it actually comes in here. and then it continues on, and it's fixed on one end. This end over here is free to move, and this is above the sensing pad underneath it. So this can move up and down, okay? And if it moves up and down, it's going to change a capacitance between this cantilever and this sensing pad underneath it. So it's like a capacitor. If you've studied a little bit about electronics, you know what a basic capacitor is. It's two metal plates, and you put a charge between it. And if you change the distance between the two plates, the voltage will change. Well, you can measure the change in voltage as this thing vibrates, and you know how much it's moved, and then you can translate that change in voltage into a force that must have imparted itself onto the cantilever. So this is actually a deprocessed analog device inertial sensor, crash bag sensor, right? So if you hit something hard enough, that cantilever will move far enough and fast enough that the circuit interprets it as, oh gee, we hit a wall or we hit another car. I better explode that airbag in the steering column. So I got to do that before, you know, the passenger or the driver's face hits the windshield. Okay, and this is an actual device that actually works. Okay, and it's a micro device, but again, it's based on a cantilever. There you go. Burn this into your head, you know, or at least be able to look at it and understand what it means, right? So K, what's that? Spring constant. E, what's that? Elastic, the elastic modulus. What's W? What's D? What's L? Can you draw a picture of it? So this might be a simple test question or multiple choice kind of question on an exam. All right, so I'm going to include a video that talks about the cantilever and how it's moving and all of that. So that'll probably be tagged on to the end of this lecture. Okay, so let's look at the resonant frequency again. So what is it in terms of hertz? Right, hertz is 1/second, cycles per second. Okay, so yeah, like I said, there's going to be another video which shows the example of a simple cantilever motion as a function of the mass added. I might just tag it. I'll probably just tag it on to the end of this lecture. I don't think I'll make it two separate videos. Okay. So we'll do the frame-by-frame description in that other video, and then I'll show a little bit of relationships between plotting the displacement of a cantilever. So a cantilever will move in time, and you can videotape it and watch it move in time. We'll give you some examples of that. So it's going to move in time, and you can look at it frame by frame and watch the motion. So you can plot displacement versus time. So where is it at a certain time or a certain frame, right? If you look at it frame by frame. And if you plot that out, you'll get a sinusoidal curve. And we're all familiar with that in music. You know, a certain frequency is a certain sine wave, you know, a certain period. We learned that in school in math, right? The sine wave, frequency of the sine wave. We learned it in physics too, harmonic oscillator. Okay, so a lot of the dynamic stuff that you're going to learn or continue to refine in your engineering education has to deal with vibrations. And there's actually a class you'll take on vibration. They call it vibes. Okay, so for extra credit, what I'd like you to do, and I'll put something in Learn, find a yardstick or a meter stick somewhere. You probably have one at home. If not, just find a long, skinny, rectangular solid of some sort. And then you can clamp it to the end of a table, and you can determine the frequency of 4 different lengths. And you do that by taking a video with your smartphone. A lot of the new smartphones now can do 240 frames per second, right? Back in the day, it was 30 frames per second, but you can determine the frequency or the frame rate of your camera. You can take that video, look at it frame by frame, count the number of frames per oscillation or the number of oscillations for so many frames, and then you can convert that into cycles per second that the thing vibrates. So you stop the video when it perhaps reaches the top of its motion, and then you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 11, 12, 13, 14, 15 frames, okay? And then it reaches the top again. So now you've gone 15 frames in one cycle. If you have 30 frames per second, you can do the math, and that's about 2 hertz. Okay, so it's going 2 times a second. If you're at 240 frames per second, then that's a lot faster. Okay, so do it for 4 different lengths. You can try different thicknesses. You can glue 2 sticks together if you want. Not required to do all of these, just do one of them. Do different widths if you can. And then you can look at frequency versus length versus thickness versus width. You'll find out that the thickness, changes the frequency, and the length changes the frequency. And then you can try adding some unified mass units. So those little clips that I show in the other video is a good system to use. You can tie on coins. That's what we did in one of my classes. We just used pennies or nickels. And you can actually look up on the web, what does a nickel weigh? What does a penny weigh? And you can actually convert it into real mass if you want to. Okay, and see if you can figure out what the elastic modulus is by looking at the frequency at 2 different lengths or 3 different lengths. And you can back calculate out what the elastic modulus should be from a couple of experiments. So this will be an extra credit for you if you want to do it, or just videotape it and analyze it a little bit. Look at you don't have to necessarily do just these and mass added. You can also look at displacement versus time and plot that, and then look at blur envelope versus time. So blur envelope is how blurry the image is in a given frame, and that tells you how far the cantilevers moved in that frame. So if you put a grid behind it, you can do velocity versus time. And that video I'm adding on will show you that in more detail, and it'll hopefully become clearer. Okay, and if you have any questions, you can always let me know. Well, that's it for this part of the lecture, and stay tuned for the second part of the lecture. This video will tell us a little bit about how to determine the frames per second when using a digital camera, or your phone for that matter. So what you want to do typically is to record digitally a clock or something with a second hand, or even a digital clock. So you acquire the video with your camera or with your phone. You bring it down to the computer, and then you look at it frame by frame. So in this example, we took a video of a clock, and we're using QuickTime, and we play it back frame by frame. So you can see when we play it back in its original speed, you can see the second hand moving. Now if we go ahead and we click the right arrow key on the keyboard until we see that the time is changing by looking at the blur of the second hand, and then we count the number of frames advancing frame by frame, we can see that the second hand will move again after about 30 to 31 frames. So you'll see that here. Now we've just gone to the second. So we know how many frames per second it is. You can also look, and camera will tell you sometimes how many frames per second. Here's an example of a cantilever with some mass added to it. You can see that we've frozen one of the frames in time and at the top of its motion. So it looks still. It doesn't move much in the frame that this has been recorded at. And from this you can tell that the cantilever is changing direction. So it's gone to its through its upward motion, and it's stopped more or less, and it's turning around and going back down through its oscillation. So you can study these things frame by frame and get a lot of information out of it. If we continue the motion of the cantilever and stop it later on, we can see here it's not very sharp. The image is blurred. This is called the blur envelope. And from this you can tell that it's actually moving a lot faster, because remember, each frame is the same amount of time. So here the blur envelope can give us an indication of the speed of the cantilever at that moment in time. Speed is found by taking the blur distance in the frame and dividing it by the frame time, which will give you the speed. The frame time is the amount of time the shutter is open in a classical sense. So in this case, we used a 30 frame per second camera. So the frame itself is 1/30th of a second. If we estimate the blur distance is about 5 centimeters, and we divide by 1/30th of a second, we get something on the order of 150 centimeters per second. As part of the tutorial, we're going to put it all together. So you set up your system in this manner. You can put little markers on the cantilever stick so you can see it better under video frame by frame analysis. And you can also put a grid in the background to do exact measurements with respect to the distance that the cantilever travels in at any given time within the video. So here you have 28 inches of a classical wood meter stick with no mass added. Now we've added 2 clips to it, and you can see that it's moving slower. Then we're adding 4 clips to it, and it's yet again slower. And so we can progress through this and keep adding mass to the end of the cantilever. And you can record the resonant frequency by looking at the frame by frame data. And when you're all done, you can collect all of that data and plot it. So you can do an analysis of frequency versus mass added. So here we see what the data will look like. You have a nice curve. It's not a linear curve. It's a nonlinear relationship. And now if you have an unknown mass added to the end of the cantilever, you will know exactly how far or how much mass you've added once you've got a calibrated system. So for example, if you put an unknown mass on the end of your cantilever and you measure 4.5 hertz resonant frequency, you can estimate how much that unknown mass weighs relative, in this case, to the standardized clip units. So here's a recap of the math for the harmonic oscillator, or cantilever in this case. So here we've got omega is equal to 2 pi the frequency, which is what you measure. K and M are the spring constant and cantilever mass respectively. So that's the general formula, and you probably learned that in physics. But what about this spring constant? What the heck is that? Well, as we learned in the lecture, the spring constant is a combination of material properties, which in this case is the Young's modulus, and the thickness of the cantilever, the width, and the length. So those two things are combined. You got geometry and material property. Now you can change the length of the cantilever and measure the frequency, the width, measure the frequency, the thickness, measure the frequency, and as we saw, we can add mass to it. We can also look at displacement versus time at any given point and plot that as well on a displacement versus time graph. So you can look at that displacement versus time graph, and if you do that for an actual cantilever, you will find that it's an exact sinusoidal curve. And if you plot the blur envelope distance as a function of time, which is equivalent to plotting the velocity versus time, you will also get a sinusoidal curve, but it will be phase shifted from the distance versus time graph.